When we consider our scientific productivity as a center, I think on the whole it's quite remarkable. And I believe that the informal working groups have played a significant share in making it so. Certainly for me, they've been truly invaluable as I have changed subjects, changed postdocs, changed colleagues through the years. It's been a wonderful way to introduce young people to the Physics Center, bring along a postdoc or two, bring along a younger colleague to Aspen, and it was such fun to do that at the beginning when we were a not very well-known place and a rather obscure place in the world of physics. It's far less necessary now, of course. I talked the other day at some length about the first workshop that was held here, which grew out of a working group. That is, three of us in Urbana, Gordon Boehm, Chris Pethick, and I had been working on superfluidity and neutron stars. Actually, Chris, I think, had already gone off to Europe. We got him to join us in the summer. And we knew that Mal Ruderman would be here, so we knew we would have a good core for discussion about the behavior of neutron stars. And that then led to a workshop, and I'd not appreciated it until Gordon Boehm went into the archives and found the progress report from Hans Bethe that this had really been a turning point in Hans's career, and his interests for the next few years were really determined at that workshop and by the work he did during the following months, trying to understand the nature of matter in neutron stars. A group of us continued to be interested in neutron stars throughout the 70s, and our interest accelerated when we realized that we did not understand what causes a pulsar glitch. A sudden spin-up of a neutron star, which for the most part is spinning down extremely regularly as it puts out energy in radio waves and electromagnetic waves. What had been observed at the time of our first workshop was a glitch in a pulsar, the Vela pulsar. Soon thereafter, there was a glitch discovered in the Crab pulsar, both very young neutron stars, and our first work on the problem had to do with explaining them as starquakes, as Gordon Boehm explained the other day. One of our postdocs in Urbana went off to work with Phil Anderson in Cambridge in 1974, and they came up with a much better explanation because by that time there were enough pulsar glitches that we realized it could not be due to starquakes. Starquakes would be far too infrequent. As was noted at the time, if we wanted to explain the glitch in the Vela pulsar, we'd have to wait 10,000 years for another glitch in order to be sure our explanation was correct. Naoki Ito and Phil Anderson in Cambridge in 1974 said, well, there's a much better possibility that neutron stars are filled with vortices because they rotate. The neutron superfluid, therefore, has vortices present in it all the time. The vortices can pin on objects in the star. In particular, they can pin on nuclei, and if they pin, then they will hold that angular momentum for some period of time until eventually they will unpin, and that unpinning is typically catastrophic. They all go at once, and that is the origin of a glitch. And following that work, then with the group that had begun to work on this, particularly with Jacob Shaham, who had been my postdoc in Urbana, gone back to Israel as their youngest full professor, With Jacob, we started looking seriously into the consequences of the proposal by Anderson and Ito. And that work almost entirely took place here in Aspen in the summer. Jacob started coming regularly. He'd come as my postdoc, but he started coming regularly because by 1976, it was clear that his son, Gil, was a prodigy in the violin. And he had his first performance here in 76 is the wrong year. It was a later year. He had his first performance here at the age of 9, so that would have been 1980, in the living room of friends here in Aspen. And it was quite clear this kid is on his way, because what he had a superb accompanist, I think it was Rita Sloan was accompanying him, and he looked at her and he said, "You didn't quite play that passage right, did you?" So Jacob would come. Phil Anderson started coming. I think he was attracted to Aspen in no small part by our work together on superfluidity and neutron stars. And one of Phil's postdocs, students actually, graduate students, Ali Alpar, who had gone to him in Cambridge from Turkey, would come as well. And we formed a small community and worked together every year through the late 70s and indeed well into the 80s on the issue of superfluid neutron stars and being able to observe that superfluidity of the neutrons and the crusts of a neutron star through glitches and, even more important, through their post-glitch behavior. And that's still an ongoing program because many more pulsars have been found to glitch, and the issue then is one of fitting the post-glitch behavior to understanding of the neutron superfluid that you find. Jacob started coming then very regularly every year because his son Gil became a student of Dorothy DeLay, and Dorothy DeLay said to Gil, "I don't want to get you too late. Itzhak Perelman came to me too late for me to have a maximum impact on him. I want to get you early." So based on that, Mal Ruderman then arranged for Jacob to move from Hebrew University to Columbia so that Gil could work full-time with Dorothy DeLay, which he did. It turned out that his younger sister Orly is as gifted in piano as he is in violin, and they are among a number of the physics kids who have gone into music. They are, I think, our outstanding success story. Let me mention one other thing that I did not get a chance to talk about the other day, and that has to do with workshops on superconductivity. We mentioned that early on, Sudeep mentioned that we had a very successful workshop on high-temperature superconductors in 1988, right after their discovery. Well, let's fast forward another 12 years or so, and a number of us realized that the kind of unconventional superconductivity that one finds in the cuprate superconductors is present as well in the so-called heavy electron superconductors. These are materials that contain local moments, F electrons, that at high temperatures are localized. You lower the temperature of the material, they hybridize with the conduction electrons and turn them into heavy electrons with masses that can exceed the mass of a mu meson. That is, they can be more than a couple of hundred electron masses. Yet they are itinerant, they do superconduct, and it looks as though their superconductivity was similar to that found in the high-temperature cuprate superconductors. There's a third class of unconventional superconductors, the organic materials, which again look teasingly similar to the heavy electrons and the cuprates. So we had a most successful workshop here in, I believe it was 2001 or 2002, 4 or 5 weeks that brought together people working in all of these different kinds of superconductivity. And I think that is one of our most successful workshops. It had an impact on the field because it started people who were working on one of those three classes of materials working on the others. And we're all very pleased, this community, that we are returning to this topic next summer with a 5-week workshop that will include all three classes of materials and perhaps a number of others. A workshop is set up ideally according to our rules. You have a set of 3 or 4 organizers at the most. They are allowed to invite another roughly 8 to 10 people who will be automatically admitted. In addition, the center sets aside for a given workshop anything from another 15 to 25 places, depending on how hot the topic is, so that you may wind up at a workshop with 30 to 40 people, all working in more or less the same field. Ideally, in keeping with the traditions of the center, you have no more than 2 sessions a week of perhaps 3 hours. And the rest of the time you should be off working together on things you've learned during those sessions or posing questions for the next session. It doesn't always work that way. Some workshops have talks almost every day. Most workshops have more than just 2 sessions a week. But we try very hard to remind people that this is not a conference. If you're having a 2-week workshop, it's not a 2-week conference. It's a time when people should have some chance to think. And of course, the reason working groups are so effective is that typically these are 5 or 6 people coming together, continuing a collaboration. We would have really made minimal progress on superfluidity and neutron stars were it not for that series of meetings of this informal working group through the 80s, late 70s, and the 80s. And in the same way, I ran a meeting this summer, which was not in Aspen, in Snowmass, but then arranged for a group of key people from that workshop to come over here and spend a week. And we had no lectures. We just talked every day, all day. And it was terrifically productive. And people who otherwise could not have come. Our problem is always that of getting experimentalists, and working groups with experimentalists are an awfully attractive way of bringing experimentalists here. And at workshops, we do waive our rules of people being here for a minimum of 2 to 3 weeks and permit experimentalists to come and go after a week here. Now, those rules also are broken in that you too often, have an experimentalist who comes in, gives a talk, and leaves. That should be a total no-no, but in fact it happens more than once. But the problem any theoretical institute has is that of keeping contact with the experimental community. And it's something we have to be continually working at as a center to be sure that it isn't just theorists talking to each other, but theorists talking to each other in a context of experiment and observation. What is interesting is that we were not the world center of theoretical physics in 1965, nor were we in, I would say, 72. But somewhere into the 80s, we became the world center of theoretical physics. There was kind of a phase transition in which it clearly more was happening here over the summer than in any other single location. Now, one of the people who helped make it that way was Jacob Shaham, whom I mentioned earlier. He died tragically at age 52 in New York about 10 years ago. Jacob was a marvelous combination of somebody who was enormously good at research on the one hand and had a deep interest in explaining science to the non-scientists. So while in Israel, he started a TV program. He became the Carl Sagan of Israel. He chose the topics, he chose the people, and it was one of the most watched programs on Israeli television because Jacob had such an encyclopedic knowledge of science. When he came to me, he did not even know what we would be working on, but what he did know was everything in Landau and Lifshitz, which he had taught himself, so that he was on a par with all the young students of Landau who had to pass the theoretical minimum based on the 9 volumes of Landau and Lifshitz. Jacob became a famous man in Israel and in fact throughout the world, wherever there were Israelis, so that when he would be in New York or Paris or Rome or even Istanbul, people would stop him on the street and say, "Aren't you Jacob Shaham, who runs the science program on Israeli TV?" In these times when we need eloquent popularizers of science, he is especially best, not only for his scientific ability, but his abilities to communicate.